everyone, welcome back. So in this video, we are going to talk about 3.2 trigonometric integral. So in calculus 2 so far, we've been learning many different types of integral techniques because we have so many different type of functions. Therefore, depending on the function, we've been utilizing a different type of integral technique, right? So what we're going to do in 3.2, we're going to deal with trigonometric function and how to take the integral. We're going to focus on that idea. So here is the concept that I want to introduce. So we talked about IBP method, integral, by part. When you have a product of two functions, we've been utilizing IBP that we learned in 3.1. So now, what if I have two functions? One, in both of function is a cosine and sine, or it could be any trigonometric function. What if I have, product of sine and cosine? How would you be able to take the integral? Are we still use IBP? So the answer is actually no, because sine and cosine, it's a more complicated function, because it's not just number, it's more likely, trigonometric, geometric concepts. So when you're taking the integral of the product of two trigonometric function, in general, we are going to use U substitution. So we talked about this one long time ago in chapter 1. So here is the example. So I'm going to take a look at the example. We have two functions, sine x and cosine and sine x. I'm trying to take the integral, the product of sine and cosine. So instead of using IBP, because you have to find out the u and v and u prime v prime. It's a little bit complicated. So simple way is always u substitution. So let's see, according to the u substitution, if you remember, you're going to say one of the function is u. So let u equal to cosine x. And then you're going to find out sine x times dx in terms of u variable. So if you remember u substitution, we're going to take the derivative, du over dx. So take the derivative of cosine x, it's going to be negative sine x, correct? So that we know du is equal to negative sine x dx. In other words, negative du is sine x dx. Exactly, this is what I want. Sine x dx, now it goes to negative du. So according to the u substitution, it is going to be cosine x is u, sine x times dx is du. So this is much simpler to take the integral. So I'm going to bring negative to the front. So you are going to u invisible 1 plus 1 divided by 2 plus c. So that we have negative u to the second over 2 plus c. And then you can go back to the x variable, cosine x to the second over 2 plus c. So we talked about how to utilize and when you can use u substitution. So it can be applied into the sine or cosine product. So that was a simple question. There was a simple, step you can think about. Now what we're going to do, what if you have, so this is a simple thing. So now we're going to do a little bit challenging step. What if we have some exponent, one of the sine or cosine? So what I'm saying is, you can see the next slide. It's not just simply sine x times cosine x. Now I have a sine to the exponent. So it could be sine to the second power. It could be sine to the third power. So one of the function has an exponent. Are we still using u substitution? Yes, because it's obviously, this means sine j to the x means sine x outside j. So you can see that one is the whatever the j power and sine x has been solved. So definitely you can still use a u substitution. So we're going to keep using the u substitution whenever you see the product between sine and cosine. So now I see that some sine x has been subbed into the j power function. So we're gonna keep going. Let u equal to sine x because that has been subbed. So take the derivative, which is a cosine x in this time, positive cosine. And then du will be cosine x dx. So exactly we match cosine x dx, that is a du. So if I rewrite it, that means u to the j, correct? Because sine x has been subbed. And then we have cosine x dx, that's a du. So according to the integral, u j plus 1 divided by j plus 1 plus c, you can go back to the x variable. U was sine x to the j plus 1 over j plus 1 plus c. So we can generalize the outcome of the integral for the integral of the products between two functions, sine and cosine, especially when sine has an exponent. So if you have a sine to the second power, you're gonna just plugging in 2 into the j so you can find out the answer simply, okay? So keep in mind, we are just trying to generalize what the outcome when you have a sine has a power and still it is multiplied with cosine x, okay? So likewise, we can think about in the next time, here, we have still cosine times the sine x, but in this time, cosine has a power. So it doesn't matter, we see the structure, cosine has been subbed. So this means cosine kth power x means cosine x outside k. So we see that there's a kth power function and cosine has been subbed. So I can say let u equal to cosine x in this time. So take the derivative. So cosine x will be negative sine x. So that du will be negative sine x times dx. In other words, negative du equal to positive sine x dx. That's exactly what I'm looking for. Sine x dx will be negative du. So that means integral u to the k, right? And then sine x dx, that's negative du. So I can bring negative to the front. U to the k du. So now it is negative u k plus 1 over k plus 1 plus c. You can resubstitute in terms of the x variable, negative cosine x to the k plus 1 over k plus 1 plus c. So this is a general form when you have a power of cosine x function, okay? So something is getting better and better. So what I'm saying is, let me just create an example. So now I have an example. Let's say we have a sine second power times a cosine x dx. So we already know whenever you have a power of the sine x function, you just increase that. So this is a general form. So what happened? We already know this is the same as sine x to the j plus 1 over j plus 1 plus c. You're going to simply plugging into the j, right? So that sine x to the third over 3 plus c will be the outcome simply. Does it make sense? Because we don't know what the j or k will be. So now j is a 2, so you're going to plugging in and you can simplify the answer. Same thing, if I have a cosine 3x times the sine x dx, we know that the general form is going to be negative cosine x to the k plus 1 over k plus 1 plus c. Now your k is a 3, so negative cosine x 3 plus 1, 4 over 4 plus c. That's your answer. So you can simplify the answer because we just proved that what the general form of the product between two functions, especially when there's a power of sine and cosine. So we keep using the u substitution when you have a sine and cosine product instead of using IVP. Okay, so we're gonna keep building this idea. Are you guys okay with that? So now we have a a more challenging question. Ooh, are you guys ready? So here we go. So in this step, what if I have, okay? What if I have the power in both cosine and sine function? So I'm gonna have j and k both, right? So in the previous slide, I show you one of the trigonometric function. So either sine has a power or cosine has a power, but now I have a power on both cosine and sine. Dun, 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 dun. We're not gonna give up, we're gonna keep thinking. So one of the technique you can think about, the Pythagorean identity. Pythagorean identity is very popular if you remember. So Pythagorean identity says that, oopsie. Sine, if you remember in trigonometric function, sine x second plus cosine second x is always 1. So I can modify this one. Sine second x is the same as 1 minus cosine second x, or cosine second x is 1 minus sine second x. So just keep in mind, these identities might be helpful when you're taking the integral of cosine x sine x, the exponent of both function. So I'm gonna show you. So here is the case, okay? So there is a Pythagorean theorem, and then we have to think about a couple things. Sometimes k could be even number or odd number, or j could be odd number or even number. Depends on the, even or odd, we might have a different cases. So let me show you that cases. So anyway, we are trying to find out the general form when you have, power on both cosine and sine functions. So here's a case one. When k equal to odd number, okay? So odd number can be written by even plus 1. It's always an odd number. So k is gonna be for cosine x. So what I'm gonna do, I'm gonna plugging in 2n plus 1 into the k spot because I'm looking at the case when k is odd number. So integral cosine 2n plus 1 x times, and then sine, I'm not gonna touch, just I'm looking at the case when k equal to odd number in dx. And then I can think about this part, so I'm gonna highlight this. Cosine 2n plus 1x, we can separate it. Cosine 2n x times cosine x, because if you remember, a to the b or a to the x times a to the y, you have a same base, you can adding the exponent according to the exponential property. So same thing, we can utilize cosine x, 2n plus 1, I can break them into 1 is a 2n and invisible 1. So 2n plus invisible 1 is a 2n plus 1. There's invisible 1. So that means this is, I can rewrite it. Cosine, you can have second power inside and you can separate n because a to the n times x, same as a to the nx. So I can have a 2 inside. So let me write it again. 2 inside. And then you have n outside. So we can separate it first. And then I have 2 inside and n outside. So we have a keeping cosine x right there. And then I'm going to write the rest of information. So have a sine j dx, integral sine j dx. And now, whoa. Do you remember cosine second x is the same as 1 minus sine second x according to the Pythagorean identity. So I'm going to rewrite it. This is the same as 1 minus sine second x outside n, and we still have a cosine x, and then we have integral the rest of information sine j. Oh, I forgot the x everywhere. Sine jx and dx. Are you following? Now we are doing so far so good. I'm going to look at this structure. here, sine to the j, sine jx, which means j is a power, and dx. And then when you look at this one, so now sine is definitely the sub function, because this one, we have a j power function, and sine x has been sub there. So you can look at this part, and then we're going to use a u substitution. So you're going to find out cosine x times dx in terms of the u. So let me see what happened. Here, let u equal to sine x. So du over dx equal to cosine x. So we know du equal to cosine x times dx, which is we are looking for. Cosine x will be du. And then what happened? We just finalized that here. Sine x is a u. So we can rewrite it 1 minus u to the second to the n. And then sine x is a u, so u to the j, cosine x dx has been du. So this is the general form when you have all the exponent for the cosine function. Okay, so that's the case. You can consider like now the k could be the even number. You can keep finding out the generalized form when k is an even number or j is an even number, something like that. But I'm just checking when the k and j are odd case. So something we find out the general form. Good. I'm gonna keep doing this work. When the second case, let's say this time j is the odd number. So same thing, 20 plus 1 for sine function. So we're gonna keep going. So that is going to be cosine k. I'm not gonna touch cosine, and then sine 20 plus 1x dx. And we know this part, we can break them into, what happened? You can break them into sine 2nx times sine x. That means sine second inside and outside and sine x. So you can keep going, and sine second x, we know 1 minus cosine second x according to the Pythagorean theorem. So that's a good, we got this. So I'm gonna highlight it. So this is to break those two. And then 2 is inside. And then sine second x is the same as 1 minus cosine second x. It's a little bit hard to look at it. So let me change the color. So sine 2n x, sine second x inside, outside n. Sine second x is the same as minus 1 minus cosine second x and n. So I'm going to keep writing the rest of information. Integral cosine kx and dx, cosine kx dx, cosine k power x dx. Now, we know that cosine x has been subbed into the k power function, so we can do the same thing. Let u will be cosine x, so du over dx equal to negative sine x. So du will be negative sine x dx, and exactly we have here. All I need is sine x times dx. That is going to be negative du. So now we have pretty much everything. What happened? Cosine is a u to the k. 1 minus u to the second, because cosine is my u. And sine x dx has been negative du. So I'm going to bring negative to the front. So u to the k, 1 minus u to the second to the n du. And this is a general form when j is the odd number. So you can think about like other cases when k is even and j is even, but I just want to give you the idea. You can think about both k and j are going to be the odd number, and then you can generalize the integral in this format. So sounds like a little bit abstract, but I think you are getting into. So I'm going to show you the real problem. I'm not going to just use a k and j as an abstract symbol. Let me give you the specific number, and then you will see what's happening. Okay, so this is a very general idea when you're multiplying the two trigonometric functions, especially sine and cosine, and then both of them has a power. Okay, so there is a general form, but the actual problem is much simpler. Okay, so let me show you that example right there. This is exactly what I want to show you. So you see that I have a 3, I have a 5 on both the cosine and sine. So now we know what's gonna do. So you can now, the 3 is odd number, 5 is odd number. So I'm gonna, you can use a sine or cosine, doesn't matter. You can break them one of the function. So let's say I'm gonna break cosine third. So it could be same as a cosine to the second x times a cosine x, correct? And then you're gonna keep sine fifth x. I'm not gonna touch other function. So I just break cosine third, one is a 2 and another one is 1. So that's the same. And then why? Because of cosine second, this one is the same as 1 minus sine second x according to the Pythagorean theorem. So therefore, they're going to be same. And then we have cosine x, sine fifth x, and dx. Getting better. And then we know that according to the above the proof, we are going to find out the sub. Where is the sub? Sine x has been sub into the fifth power. Sine x has been sub into the second power. So let u will be the sine x. So du over dx will be cosine x. So du will be cosine x times dx. So exactly you are matching cosine x times dx. That is going to be du. Now we can finalize it. Integral 1 minus u to the second, because the sine x is a u. And then we have u to the fifth. And then cosine x dx has been du. So now this is exactly better form to take the integral. So I'm going to do the distributive property. U to the fifth, u to the seventh, du. So we are going to separate it. U to the fifth du minus u to the seventh du. So when you take the integral, u to the fifth plus 1 over 6 minus u to the 7 plus 1 over 8 plus c. So that's going to be close to your answer. And then u to the 6 over 6 minus u to the 8 over 8 plus c. And you can go back to the x variable. U was a sine x to the 6. So that's actually better form of your answer. How you think? Yeah. So since we proved that if you have odd number, break them. One is an even number second, because we are going to use the Pythagorean theorem so that in that way you can find out the subfunction. Okay, so to do this question, I've been explaining the above proof stuff to find out the general form. Okay, so I'm going to keep practicing one more example, the following. So let me actually get rid of this one because I don't know why the power reducing form. Okay, so we're going to go to the second question. Okay, same thing. So we have a second and third. So this is odd number. I'm going to break this. Okay, so what are you going to do? This is going to be integral cosine second x, and this one sine second x times sine x, right? That's the same as a sine to the third. Are you okay? So I'm going to highlight it. Sine third x has been sine second. One is the second power and sine x. Now we know this is according to the Pythagorean theorem, right? We can say this is the same as 1 minus cosine second x. And then we have the same thing, cosine second x, sine x, dx. They're same. Now you see, obviously cosine has been subbed into the quadratic function. So let what? Let u equal to cosine x, du over dx. That is a negative sine x. You take the derivative of the cosine. So that is going to be du will be negative sine x dx, correct? But I'm looking for exactly sine x dx in terms of the u variable. So negative du will be sine x dx. Great. So finally, we can rewrite it. Integral cosine x has been u to the second, 1 minus u to the second, and that is a negative du. So negative u to the second, 1 minus u to the second du. We know this is a better form to take the integral, right? So therefore, negative u to the second minus u to the 4 du. So you can separate it, negative integral u to the second du. And we have a minus integral u to the 4 du, right? Because this negative in front of the integral. So now if you take the integral negative, u to the third over 3, because 2 plus 1 divided by 3, minus u to the fifth over 5. And then now you're going to do the distributive property with the negative. So negative u to the third over 3. Negative, negative, change to positive. And then you can change back to the x variable. Minus cosine x to the third over 3. Cosine x to the fifth over 5 plus c. So that is your final answer in terms of the x variable. How you feel? So let me just get rid of this a little bit. So you can, take the integral of the product of the two functions, especially sine and cosine, even though you have multiple powers of it. Okay, so that was a good practice, and we're gonna keep going to do the next idea. So the 3.2 is a very short topic, so I'm pretty sure you guys can do better and better. So let's take a look at the next idea. Here we go. So in this slide, I want to introduce another identity. So you observe that Pythagorean identity is a pretty necessary thing when you look at the multiplication of two trigonometric functions, sine and cosine. Another identity is here. It's a very important identity, power reducing identity. So we already know, according to the Pythagorean theorem, so let me write it. So Pythagorean identity said sine second x plus cosine second x equal to 1. So cosine second x is the same as 1 minus sine second x, or sine second x is 1 minus cosine second x. We already know Pythagorean identity. So there's another way you can simplify cosine x second, sine x second. So cosine second x also same as 1 over 2 times 1 plus cosine 2x. So keep in mind, this is another identity. You can reduce down the second power. And then sine second x, you can reduce down the power, making it equal to 1 over 2, 1 minus cosine 2x. The difference between Pythagorean identity and power reducing identity, look at that. Cosine second x is the same as 1 minus sine second x, but you still have a second power. I want to get rid of the second power. If you want, you're going to use a power reducing identity. So instead of saying cosine second x is equal to 1 minus sine second x, cosine second x, according to the power reducing identity, is 1 over 2 times 1 plus cosine 2x. There's no more second power. Same thing, cosine second x is going to be no more second power because it is the same as also 1 over 2, 1 minus cosine 2x. So keep in mind, okay, there's many identity, but these two are going to be pretty helpful. So let me show you the example. Why should I have to use this power reducing identity? Because of this reason. In this example, what's going on? We have integral sine x second x dx. I'm trying to, take the integral. So you feel like, oh, Professor Ben, I feel like sine x has been subbed into the quadratic function. So let me try it that way. Let you want to say let u equal to sine x. So du over dx equal to cosine x. Du equal to cosine x dx. So you might be saying, oh, cosine x dx is not there, right? So you feel like u substitution is not going to work because there's no du. We cannot convert dx in terms of the du because there's a missing information. Or you might be thinking, Professor Ben, maybe I can change, sine second x is the same as 1 minus sine second x and take the integral. Okay, let's try. So in this time, well, actually it's the same as cosine second x, right? So I'm trying to show you many different ways. We failed to use a u substitution because we don't find out cosine x dx. So now I'm going to use a Pythagorean. So u substitution failed. And I'm trying to use a Pythagorean identity, which is a sine second x the same as a 1 minus cosine second x. So we know in this time cosine x has been subbed into the quadratic. So you want to say u equal to cosine x. So du over dx equal to negative sine x. And then du equal to negative sine x dx. Whoa. I don't have, there's a no negative sine x. Or here, there's no negative sine x. So Pythagorean identity is also fail. Right? It's not going to work. So Professor Ben, how do I solve this question? So in this time, we're going to use power reducing identity. Using u substitution, Pythagorean identity, I don't see where is it, du. I cannot convert it, right? So therefore, we're going to say, instead of sine second x, either Pythagorean identity or u substitution, we're going to use sine second x is the same as this. So therefore, it's the same as sine second x. What did I say? 1 over 2, 1 minus cosine 2x. Maybe we can take the integral in this format. I'm going to do the distributive property. So it is going to be same as integral 1 over 2, right? I can actually bring 1 over 2 to the front, right? Because this is the number. So let me just bring the number to the front. So we have 1 over 2 integral 1 minus cosine 2x dx. And then I'm going to separate the integral 1 over 2 integral 1 dx minus integral cosine 2x dx, right? So it looks like we are able to solve it. So now let's look at it. I'm going to take the integral. This is going to be x minus, don't you remember here? Don't forget that how you take the cosine 2x. I'm going to write here if you forgot. So cosine integral cosine nx dx is the same as 1 over n cosine nx plus c. So we have here cosine 2x will be sine 2x, and you have a 2. This is a chain rule. It's a 1 over 2. That's it. So then we are going to finalize it. So 1 over 2. Now I'm going to, distributive property x minus 1 over 2 times 1 over 2, 1 over 4 sine 2x plus c. Then you can solve it by using the power reducing identity. Because we observed that substitution, Pythagorean identity, those are fail. So using another identity that is equal to cosine second x to sine second x, it's going to be helpful. That's pretty much, okay? So 3.2, we are introducing a couple identities. So let's take a look at one more example. So here, I have a similar example. So we already know that we have a cosine second x. So if you try to use substitution, Pythagorean, they're going to be fail. You can check if you want, because we already did the similar work in example 5. So instead of using those method, I'm gonna use power reducing identity, because cosine second x is the same as, so integral cosine second x dx is also same as, what is it? 1 over 2 integral 1 plus cosine 2x. So we can use a power reducing identity instead of using use substitution or Pythagorean because they're going to be failed. So now what are you going to do? We're going to take the integral. So I'm going to bring 1/2 to the front. So I'm going to minimize it a little bit. So here, 1/2 integral 1 plus cosine 2x dx. So it's the same as a 1/2 integral 1 dx plus integral cosine 2x dx. So if you want, I'm going to bring here and minimize it. So it is going to be 1/2. This is going to be x. This is going to be, go back to the integral. Cosine will be negative sine, keep 2x, and then chain rule 1/2. So therefore, if you do the distributive property, 1/2x minus 1/4 sine 2x plus c. So you can solve this question by using power reducing identity. Getting better, better, better. Are you happy? Okay, so we got that. That's a pretty, I don't want to say simple, but that's pretty understandable topic we got. So there gotta be a way you can take the integral, the product of sine and cosine, and I show you a couple identity you can utilize. Sometimes you can use substitution, sometimes you can use a Pythagorean, or sometimes you can use a power reducing identity. So please organize them. The next idea is the last idea. So let me go down slowly. Okay, but I'm gonna make a little bit of space for you to summarize. So what I'm saying is there's a couple, so you have a sine x, cosine x, there could be k and j, whatever. You could use the Pythagorean, or you can use it simply, use substitution, Pythagorean identity. Depending on the structure, you need to choose one of them, power reducing identity. So look at the above example. I show you exactly when you can use a use substitution, Pythagorean power reducing identity when you're multiplying sine and cosine with the power. Okay, so check that case. All right, the last case, dun, 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 dun. Exciting. Here we go. The next one, what if I'm multiplying tangent and secant, right? So there is no information from the integral table. They don't show you the outcome, what the tangent x times the secant x. So we have to think about it. So here's a couple things you already learned. Step one, we already know the derivative of the tangent is a secant x. We proved that in chapter 1 and calculus 1, or you can find out from the table. So in other words, if you take the antiderivative of the secant x, you will go back to the tangent, correct? So this is the derivative and this is the integral, right? So this makes sense. Derivative and antiderivative integral, there's opposite. So tangent x, so when you take the derivative, it's going to be secant x. Integral of the secant x, you will get back the tangent x. So same thing, if I take the derivative of the secant x, we already know that from the table, it's going to be secant x times this tangent x. So this is a derivative. Same thing, if you take the antiderivative of the secant x times the tangent x, you will get back the secant x, correct? So this is just so obvious. You can always find out this information from the table. And then one thing, if you take the integral, right? So take the integral of the tangent x, not the reverse. We also proved that it is going to be same as ln secant x. And then if you take the integral of the secant x only, it's going to be ln secant x plus tangent. So these are from the table. So you can find out this information from the integral table. Also, you can just think about it from calculus 1 and 2 relationship. And then just one more thing I want to talk about it. We already know the Pythagorean identity. So these are Pythagorean identity. Cosine secant, x is the same as 1 minus the second because it is from sine secant x plus cosine secant x equal to 1. And also you need to think about it. Tangent secant x minus or tangent x plus 1 equal to always a secant x. This is another Pythagorean identity getting involved with the tangent and secant. So these are, remember, very, very important. I'm going to highlight the last one here. So we're gonna just recall. This is a recall from your trigonometric course, geometry, calculus 1 and 2 so far, right? So we're gonna utilize these identities to solve tangent, okay? Tangent integral, okay? Multiply with the secant or tangent secant. So let me show you that example. Dun, 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 dun. So here, they want you to take the integral tangent secant x. The problem is integral table does not show us the outcome. Dun, 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 dun. So we use trigonometric identity that you know. So trigonometric, you can think about one of the identity is a Pythagorean identity. As we saw, tangent secant x is the same as secant secant x times secant x secant x minus 1. So what I'm going to do, because we don't have any information what the tangent secant x from the table. So we're going to utilize the identity. I do know this is the same as secant secant x minus 1 dx, correct? So we already know this is the same. Tangent secant x same as secant x minus 1, according to the Pythagorean identity. So now I can separate it. This means secant secant x dx minus integral 1 dx. So what do you know? Integral secant x, we already know from the table right there. Integral secant secant x, this is going to be tangent x, and then this is going to be minus x plus c. So you can find out the answer very, very simply using those, all the recall from the table and identity case. Are you okay with that? So I'm gonna keep building this idea. Secant secant x, we already know from the table. So this is so obvious, you know, identities and properties. So let's take a look at another example. Okay, now I'm gonna increase the exponent from 2 to 3. Dun, 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 dun. Here we go. So this is the odd number. So I cannot use a Pythagorean. So I'm gonna break this one because the Pythagorean always have a second power. So it is the same as tangent secant and times a tangent dx. So we know now tangent secant x is the same as, according to the Pythagorean, secant secant x minus 1. So I'm going to change this. Secant secant x minus 1 tangent x dx. So these are same. This is a Pythagorean identity, correct? So now here, very similar. Now you might be able to use a u substitution because the secant x has been subbed into the quadratic function. So I'm going to say, let u equal to secant x. So du over dx, what is it? Go back, du over, you're going to take the derivative of the secant. It's going to be secant x times the tangent x. So secant x times tangent x, that means du is secant x times tangent x times dx. Are you okay? So in other words, we are looking for what the tangent x and dx. I can modify this divided by secant x on both of sides. So what happened? We can say du over secant x is, gotcha, tangent x dx. So I can modify this one, correct? So let's rewrite all the information slowly, surely. So let me minimize a little bit. So therefore, we can finalize what happened. This one, I'm gonna bring a little bit here. So this is from, yeah, this is there. This is here, right? So now what happens? Secant x has been subbed. So you can say u secant minus 1, correct? And then tangent x dx is the same as 1 over secant x du. And we know secant x has been u. So this is the same as, again, u secant minus 1, 1 over u du, because the secant x is a u. So now you can use a distributive property. Integral, let's just cancel u minus 1 over u du. So that means you can separate it, u du minus integral 1 over u du. So this is u 2 over minus, make sure this is ln, don't forget that, ln u. So the final answer will be, you can leave it at u, or you can go back to the x variable, secant x, or you can write it secant, u was a secant x a second, over 2 minus ln secant x plus c will be the final answer in terms of the x variable. So remember, 1 over u is ln u. So that's, you can keep utilizing, many identity we talked about and all the mixed information. Okay, so don't worry, we're gonna keep building. So this is the case when your integral is getting involved with the tangent or secant or both. Okay, so let me show you the next case. What if I have both the secant and tangent? Okay, this is the 5. I don't like the odd number because even number is always better, right? So let me break this into secant 4x times secant x and tangent x. So obviously you can see secant x has been subbed into the 4th power function, correct? So let u secant x again. So du dx, we know if you take the derivative of the secant x, will be secant x tangent x. Another means du will be secant x times tangent x dx. And then we want to find out what the tangent x dx. You're going to find out, wait. But in this case, we have secant x times tangent x and dx. Exactly, we have everything. Those are going to be du. Gotcha. So what happened? U to the 4, that's a secant, and these all 3 has been du. Bum, 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 bum. So let's take the integral 5, because you're adding and divided by that, c. And then now you can go back to the u variable and to the x, secant x to the 5th, over 5 plus c. Boom, 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 boom. We got the answer. How you feel? Okay, so you don't need to scare off nothing, okay? You have all the tools. You have all the techniques. You have to think how and when you're going to utilize it. So let's keep, taking a look at the next one. I have 6 and 4, okay? So now I have, think about it, because, second power is always better. So you have to think about it. To use a Pythagorean identity, which is a secant x equal to tangent secant x plus 1, or tangent secant x equal to secant x minus 1. These are Pythagorean identity. I'm going to break this into second power. So what I'm saying is tangent 6x, leave it there, but secant x, same as a secant 4x. So we can do that. And then what happened? You're going to change the secant x is the same as a tangent secant x plus 1 of them. So integral tangent 6x, this is the same as tangent secant x plus 1. And I'm going to keep the rest of them. Why? Because I see now tangent x has been subbed into the quadratic or 6th power function. So let u equal to tangent x. So du over dx, we know that if you take the derivative of the tangent x, go to table, it shows you secant x. So du equal to secant x times du. Exactly, this is what I want here. That's going to be du. We got you. So now we know tangent is u, so u to the 6, u to the second plus 1. The secant x dx is du. Now we know what's happening. So integral u to the 8, u to the 6 du. You're going to take the integral u to the 9 over 9, u to the 7 over 7 plus c. You can go back to the x variable, which is a tangent x to the 9th over 9. Tangent x to the 7 over 7 plus c. So you can make it simpler, simpler, simpler. How you feel? Does it make sense to you? So the more you practice, the better you have, or the better you feel, because you're gonna gain a better confidence. So one last question for today. Here we go. I'm pretty sure you can try this. So 5 and 3, you can break this to the even number. There are so many ways. I'm going to break this. Tangent 4 times tangent. Oh, there's x. Because the 5 can be 4 plus 1. And then secant 3, 2 plus the secant 1. So now the reason why, up, we know this identity. Pythagorean identity. Right? So according to the Pythagorean identity, think about it. I can also change everything to the second power. So integral, this is the same as tangent second and second double. So say it's going to be 4 tangent x. And then I can have secant x plus, oh, not the plus, my bad. It's just, multiplication. So there is a secant and dx. And then you're going to think about it. One of the tangent second or secant second, you can convert it to another, Pythagorean theorem. So I'm going to use the second one because tangent secant x is the same as secant x minus 1. And we have a second power. Just be aware. Tangent 4, same as tangent second. And then tangent second inside, it's going to be secant x minus 1. So the rest of that I'm going to keep writing. Tangent x, secant x and dx. Okay, keep thinking. Now what are you going to do? You see now better, secant x has been subbed into the second power. So this is a sub. Let u equal to secant x. So du over dx, got you. This is going to be secant x tangent x. Du will be secant x times tangent x times dx. Do I have that information? Where secant x tangent x, secant x tangent x dx, they are going to be du, correct? So you can say, now secant x is my u. So u secant minus 1 outside secant. And then here's a u another secant. Tangent secant dx, that's going to be du. Please expand all the parentheses. So u to the 4, because that means u secant minus u to the second, you multiply same thing. So it's going to be 2 u to the second plus 1. And I have u to the second du. I'm going to minimize it a little bit. So then u to the 6, 2 u to the 4, u to the second. Distributive property. So now you're going to take the integral u to the 7 over 7, 2 u to the 5th over 5, u to the 3 over 3 plus c. Again, you can go back to the secant, because that's my secant u. So therefore, secant x to the 7 over 7, 2 times secant x to the 5th over 5, secant x to the 3rd over 3 plus c. That's your beautiful answer with the x variable. Awesome. Are you okay with that? So we explore how to take the integral when the function is getting involved, still the product of two functions. But in this time, we talked about sine x times cosine x case, or tangent x times secant x case, or there are variety like a tangent j case or secant k case. There are many ways, but think about the identity that I introduced today. Pythagorean identity is pretty helpful. Power reducing identity is also helpful, and use substitution is also helpful. So I show you all the cases you can simplify in taking the integral. So take a look at all the examples. So please go to 3.2 quiz. They're also available embedded video to explain each question. So we have available resources for you. Try the 3.2. And if you have any question, feel free to participate in discussion chapter 3. That's your participation point. Also, that's where you can engage with other people. Also, if you still need help, you can email me. We can talk to each other during my optional meeting time. So feel free to email me, and I will see you soon in the next video. Thank you, everyone. Bye-bye.